Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome to our viewers from around the world. Thank you so much for joining us. Please let us know in the comments where you're watching from. Also, welcome to listeners on the podcast version of SETI Live, available on most podcast platforms. The center of our galaxy is one of the most extreme environments we can observe, and yet it's also strangely quiet when it comes to pulsars. That's the mystery we're unpacking today. I'm joined by William J. Welch Postdoctoral Fellow Karen Perez, lead author on a new study detailing the possible discovery of a pulsar near the core of the Milky Way. Thank you, Karen, for being here.
Yeah, thanks for having me. I'm excited to finally share these results and paper with folks around the world.
Well, congrats on the fellowship and welcome to the SETI Institute.
Thank you.
So, all right. Why is the Galactic Center such a big deal scientifically? So what makes this a compelling place to study?
Yeah, so the Galactic Center is actually one of the most energetic regions in the Milky Way, the most energetic region in the Milky Way, and so that paves the way for lots of there's many star clusters in there. There's a high amount of star formation, lots of stellar evolution happening. Hence, when stars reach the end of their life cycle, they die, go supernova, some of which turn into pulsars. And so for many years or decades since the 1990s, I believe, people have been pursuing surveys towards the Galactic Center to search for pulsars. And there's been lots of estimates done that based off all these calculations, there should be a large population of neutron stars in the Galactic Center.
All right. Well, let's start with Pulsars 101. Just let's kind of introduce the audience to this in case they're not certain. What exactly is a pulsar? You mentioned supernova and dying stars. So how do we get a pulsar out of that?
Yeah, so a pulsar is a highly magnetized rotating neutron star. So a neutron star is again one of the things that can happen when a star dies. I believe a star must be between 8 to 25 solar masses in order to become a neutron star or a pulsar. It becomes a highly magnetized star with really precise rotation periods. And so it's emitting beams of electromagnetic radiation, most often in the form of radio waves that come from its magnetic poles. And when these beam crosses our line of sight here on Earth, we detect a pulse. Like the usual analogy that's made is like a lighthouse. So like a cosmic lighthouse is what people usually use.
That makes sense. So that kind of is that it sort of gets into why we use these as what we call cosmic clocks. So what makes them such great cosmic clocks?
Yeah, so pulsars actually have one of the most stable rotation periods. They often rival that of like atomic clocks here on Earth. They can go up to like microsecond precision, sometimes even nanosecond precision. So you can imagine, like I mentioned, when a pulse arrives here on Earth, we detect a pulse of arrival. And if you compare that pulse to all the consequent pulses, you can imagine that there might be like a tiny deviation in the pulse of arrival time. Um, and so these deviations determine the level of precision that you can arrive to essentially.
Oh, okay. So what makes pulsars near a supermassive black hole like Sagittarius A star at the center of our own galaxy especially valuable?
Yes, so what I failed to mention earlier is that at the center of our galaxy, you have a 4 million solar mass supermassive black hole, right? So that's huge. Um, and you can imagine that such a large black hole would obviously create a large amount of gravity around it. So this gravity environment would cause the warping of space-time. And you can imagine that if you have this tiny pulsar compared to the supermassive black hole orbiting the black hole, it would experience some of the space to warp time. So hence the pulses that would arrive on Earth would either be arriving a little bit earlier or a little bit later. Um, and this would allow us to again measure that precision that I was talking about earlier, with in terms of the pulses. and you can measure this precision and these poles of arrival times, and then compare them to that which is estimated from Einstein's theory of general relativity. So then you would be able to compare these two to be able to test that out.
So, like most astrophysics and cosmology, it all comes back to Einstein's general relativity. So what would this help us test? Gravity, space-time, the properties of our black hole?
Yeah, it would help us test all of those: gravity, relativity. Ideally, if you were to measure and time a pulsar around a galactic center orbiting the supermassive black hole, this would go on for many, many years. And eventually people may be able to like derive the mass and spin of the black hole. But that would be after like very careful timing measurements over a long time.
All right. Well, that's pulsars and why we're interested in having them in our galactic center. So let's look at the problem with our galactic center. Astronomers have predicted that there should be many pulsars near our galactic center. Why have they made that prediction? What's the assumption here?
Yeah, so like I mentioned earlier, the galactic center is the most energetic region in our Milky Way, so there's lots of star formation happening.
Mhm.
So just from that sheer amount of star formation, and again, when stars go through their life cycles and go through the stellar evolution process and die and become supernova, and then turn into pulsars, this is where those estimates are generally coming from. It's also estimated that about 10% of all high mass stars reside within that inner region of the galactic center. So this is also um, one of the facts leading us to that estimate.
So, but we haven't seen them. Where are they? Why have so few of them been detected so far?
Yeah, so it's actually very hard to um, look at the galactic center with the radio. There's a large amount of like turbulent ionized gas between us and the galactic center, um, which contributes to this thing called scattering. So scattering is um, actually causes broadening and smearing of pulses that we detect, and
Mhm.
this broadening and smearing um, gets worse at lower frequencies. So if we observe like at 1 to 2 gigahertz, you will probably not detect anything at the galactic center, which is why we're going up to much higher frequencies, 8 to 12 gigahertz, for example, for this survey, to try and avoid those scattering effects. I guess if for the math folks out here, scattering scales as frequency to the minus fourth power. So there's an inverse relation where you want to go up to higher frequencies.
I am not a radio astronomer. I admit to this. Can I get a little I don't know, explain it like I'm five on how radio astronomy works in this context?
Um, in the context of scattering, you mean?
Yeah.
Um, yes. So um, I guess it's a bit hard to explain. Um, but I guess essentially the thing you have to know is just that scattering is worse at lower frequencies compared to higher frequencies, and this
And
has to
just
do with like the pulsar spectra, and things like that. Maybe it gets a bit too scientific.
that's fine. Radio astronomy is does tend to be a very technical topic around here. So I completely get that part. I'm going to welcome in some viewers. We've got some really great locations going on here. And let me thank the Ordo Fraterna Fibonacci for their $50 donation and for watching
That's a cool
from.
username.
It is a really cool username. I love it. They're one of our regulars here, and I really do appreciate the $50 donation. And also, they're watching from Mercer Island, Washington, and Vancouver, BC, because there is a very small place that is sort of both. Really cool. All right, we have people watching from. Let me get back here. New Hampshire, North Carolina, California, Sweden. Uh, More Sweden. Wow, two from Sweden. Mexico, a couple from Texas, Canada, Montreal this time, Italy, Michigan, and another one from Canada. This one's in Toronto, and Florida, Colorado, Pennsylvania, and someone who is watching from out at sea. So once again, thank you so much, everybody, for joining us today and watching from, wow, clearly around the world, and someone from the UK. Okay. So this is, becoming quite the global show, and we do appreciate all of you being here. Again, my guest is William J. Welch, postdoctoral fellow Karen Perez, who is now with us here at the SETI Institute. That is our fellowship, and we are excited to have her here. I know this research was kind of prior to you joining us, so it's very exciting for you to have this first author paper and have all of this happen. Let's talk about this particular paper and the candidate that you found, because that's what you're here to talk about. Mm-hmm. So how was this pulsar candidate identified? What instruments were involved, and what makes it compelling as a pulsar candidate?
Yeah, so we observed with the Green Bank Telescope in West Virginia. It's a 100-meter dish telescope, the largest single dish in the world that's steerable. We observed at X band, so that's covering 8 to 12 gigahertz. So again, we're going up to a little bit higher frequency so that we're sensitive to these potential pulsars in the galactic center. We conducted 11 hours total, just staring deep at the galactic center. We had 2 different epochs. Our first epoch, which is where we found this candidate, was consisted of 5 one-hour scans. And we had a extremely small integration time of 43 microseconds, which high time resolution data products of 43 microseconds, which when you're looking for these very precise pulsars, you want to go in a slow high time resolution as possible to be sensitive to them. So we detected this candidate in our first hour scan of this epoch, and we conducted some periodicity searches. We had about 5,000 candidates, among which this one interesting candidate emerged. So we conducted our searches. We used some supercomputers at Columbia University to run these searches, and then visually inspected our final candidates. The thing that stood out about this candidate, and I will go ahead and share a slide here just to show the plot, if that's okay. So this candidate, this is the plot which you can find in our paper. This is showing our candidate. It was an 8.19 millisecond pulsar. So it falls in the category of millisecond pulsars, not normal, regular, slow pulsars. We found it at a dispersion measure of 2775, which is quite high dispersion measure. This is what you expect for any pulsars in the galactic center. This again has to do with like the ionized gas between us and the center. So as you move towards the galactic center, you expect this number to be larger. The only other current pulsar so close to the galactic center is the galactic center magnetar, which has a DM of 1780. So we do expect any other potential pulsars or neutron stars near the galactic center to have a DM up to even 5,000. So we conducted these large searches covering this large parameter space. In terms of the plot, you can see a signal. It repeats twice on this plot just for visual purposes. But you can see
that's the upper left.
Yes, this.
Okay.
Oh, sorry, I don't think people can see my mouse. My bad.
No, unfortunately they can't.
So the first plot shows time on the y-axis and phase. Sorry, time on the y-axis and phase on the x-axis, and you can see that peak is where the signal is. You can see the signal is persistent across the entire 1 hour observation. And then the plot in the middle is showing our frequency bandwidth that we observed at. So like I said, this goes from about 8 to 12 gigahertz. It's a little bit blurry on this page, but if you go on the paper, the signal is much more clearer. So this candidate was persistent in both time and frequency, which and had a high DM, which are all indicative of it being a real pulsar.
Okay. So all of what you just said makes me think this seems very legit as a candidate, as a pulsar. So what still needs to be confirmed?
Yeah. So I guess we're being very careful about saying we found a real pulsar, or a true pulsar. It's only a candidate so far. It's
Mhm.
still very exciting, but the thing that would really need to happen for us to be able to say without 100%, with 100% confidence that it is a real pulsar would be we would have to redetect it, right? So we only have this one detection. Although we had 8 scans total, 11 hours total, we were not able to redetect it in targeted or follow-up observations. So what would really need to happen is redetection at the same period, at near the same dispersion measure, um, for us to be able to say that with confidence.
That seems challenging since this is already a hard enough thing to try and detect. This is work you did with Breakthrough Listen, correct?
Yes, so I did this work during my PhD at Columbia University, which just wrapped up last fall. But this is part of the Breakthrough Listen Galactic Center survey to search for technosignatures. And as part of the ancillary science, we also perform these pulsar searches.
Okay. So if you have questions for Karen, please put those in the comments. We are watching them and we are setting them aside so that we can get to them closer to the end of the show. But I want to welcome in a couple more locations. We have people now watching from the Netherlands and Australia. So, wow, very, very global once again. And Omnipotent CEO says, congrats on the PhD. So, always a
Thank you.
very big deal. All right, let's talk a little bit about why this discovery matters, why this work matters. So, if confirmed, what does this change or complement scientifically?
Yeah, sorry, we can go ahead and remove the slide from here if that's okay.
Yeah.
Yeah, so like I said, no pulsars have been found this close to the galactic center within 1 parsec. There are a few that have been found within 1 degree, which kind of leads us to believe that if there's some within 1 degree, why is there not any within 1 parsec? But again, the thing that's contributing to this, to us not detecting them, is there's just a high degree of scattering towards the galactic center. Um, but if this pulsar were confirmed or any other pulsar was detected near the galactic center, I think it would tell us that that it is true that there's a large population of pulsars in the galactic center, that we just haven't observed them for some reason, right? Maybe it's due to scattering, maybe it's because we just haven't stared at the galactic center for long enough, right?
Hmm.
Something else that we go into the paper is discussing, pulsars may, if a pulsar is orbiting a binary, any other, it could be a black hole, it could be another star, it could be a smaller massed stellar black hole. The pulsar could experience eclipses. So the pulsar might not even be visible the entire time during its orbit, right? So we may have just gotten lucky during this detection, and then it may have disappeared, for astrophysical reasons, of course. So I think it would let us know that there is a population there that's just waiting to be discovered, and we just have to try harder.
So you mentioned the possibility of a binary. Could this open the door to finding, say, a pulsar black hole binary?
Yeah. So I guess what we're saying in this paper is that this pulsar candidate could potentially be orbiting the supermassive black hole at the center. So that would be a pulsar black hole binary. It's also possible that it's just off to the edge of the black hole and it's orbiting a smaller black hole. The pulsar's orbiting a smaller black hole. It's also possible the pulsar's orbiting around a normal stellar, a normal star, a normal main sequence star companion. So there's a lot of possibilities, and we go into what the implications of all of these potentially different orbits would be if if this pulsar is real and it's out there.
So for you personally, what would be the dream scenario scientifically? What would excite you kind of the most here?
Yeah, so I think the thing driving people that are working on this topic and this field is the potential for finding a pulsar orbiting a tight orbit around the supermassive black hole Sagittarius A. Specifically, an orbit of a year or less um, would be great. So that would be the dream scenario. Maybe it's not this pulsar candidate. Maybe it's another pulsar candidate out there that is waiting to be uncovered in the next few years or so. But I think that would really help in regards to testing gravity and relativity.
All right. Well, it sounds very, very exciting. Let's see what we have. Some questions from the audience. I'm going to start with this one because I think this is a fair. I think this is a fair question to ask. It might sound a little snarky, but I do think it's fair. The general theory of relativity has passed every test. Do we really need another one?
I guess it depends what you mean by every test. Some decades ago, there was the Hulse-Taylor pulsar binary that was discovered, and that was measured for 7+ years, I believe, maybe even a few decades. And so I know that when they were looking at that pulsar binary, they did notice that the orbit had shrank, that the periastron, which is the point in the orbit where the pulsar and the binary are closest together, had advanced, and so have been some like lighter tests, I would say, but again, like you're comparing that's like a pulsar orbiting a normal star, but you're comparing that to like a 4 million solar mass black hole. So I think there would just be different implications if you were able to perform that same test on a pulsar orbiting the supermassive black hole.
Okay.
So I think you would gain different knowledge that you can't gain from other tests that have been done.
Fair enough. Fair enough. I also like this question because this kind of brings us back to, we are the SETI Institute. We are about searching for the proof of life beyond Earth, particularly extraterrestrial intelligence. So could these pulsars close to our galactic center, is there a possibility they could be a message to other civilizations? Are we monitoring this kind of activity?
Yeah, that's an exciting question to think about. Could these pulsars close to our galactic center be a message to other civilizations? I don't necessarily think that it's a message to other civilizations. However, you might be interested in looking at some of our other work. I guess this was like specifically searching for like astrophysical signals from pulsars. But I am also involved in searching for technosignatures in the Galactic Center, and we have done plenty of searches as part of this Galactic Breakthrough Listen Galactic Center survey on looking for like narrowband signals in the Galactic Center, and we're also expanding it to look for broadband signals in the Galactic Center, where you can imagine, the argument is that if you look at the Galactic Center as a Schelling point, right, a civilization might put a transmitter in the center because it might be the easiest way to contact us. So that's one of the Schelling points that we use, and again, there are several works by me and the rest of the team on technosignatures in the Galactic Center.
And to note, one thing to note here, like I've mentioned before, Karen is our William J. Welch postdoctoral fellow and is working at the Allen Telescope Array. So that is what she is doing, everybody. She is now hunting for technosignatures. So very exciting work for you and for us. Omnipotent CEO, I'm kind of curious about this one. Can you use something to isolate the scattering? Any way to lock on to, one or even a handful of pulsars?
I guess what specifically do they mean by lock on?
I think using the scattering, like isolating the scattering specifically to find a pulsar and then follow it. Observe it more than once, I would say.
Yeah, Yeah, I guess, yeah, I don't know that there's any way to specifically isolate scattering, but, yeah, I think, like I said earlier, the way to go is kind of just, um, expand on your, like, temporal coverage, right? Observe the source for as long as you can and go up to higher frequencies. So I guess the way that we're isolating scattering is by going up to higher frequencies, like, just avoiding the problem altogether.
Fair enough. Fair enough. Okay. And Omnipotent says, yes, I got that correct on what they were going for. So yay. So we're kind of getting close to the end here. Are I'm kind of curious, are fast radio bursts related to this kind of environment? I know we've done a lot of work on that as well, and that those come up a lot around technosignature searches. So are they related in any way?
Yeah, I personally haven't done any work on fast radio bursts, but they're believed to be extragalactic in origin, perhaps even coming from magnetars, originating from magnetars, which magnetars are a class of neutron star. But fast radio bursts are a bit different because they're like transient in nature, whereas pulsars are periodic.
Hmm.
Um, so I wouldn't say they're quite related to this, but the same data products that we're using for um, pulsar searches can also be used for to detect fast radio bursts.
Okay. Um, So what is next for Karen? I mean, you've got this postdoctoral fellowship, you're searching for technosignatures. What does that look like for you? What project you're working on? Are you doing anything else with this pulsar candidate?
So we do, I guess, to address the pulsar candidate question, we do have 12 additional hours of data with the Green Bank Telescope that we've began looking through. We also have some data with the Very Large Array Telescope. Um, and these are all at X-band, the same frequency coverage that we used for this Galactic Center survey. So the plan long term would be to go through those data and see if we can detect this candidate again or any other candidate. I know there's a few other groups that are also trying to do this, so again, we have made our data public. It's on our Breakthrough Listen website,
Hmm.
and anyone is open to search through it and either help us confirm this candidate or maybe even disprove it. That's part of the scientific process. Um, to answer your other question, what is next for me? So I started this postdoc in the fall of 2025. It's a 2-year postdoc, um, and I am mostly working on technosignatures now. So utilizing the Allen Telescope array, and it's like computing hardware to try and do some real time analysis on technosignature searches. As you may know, SETI Institute partners with NVIDIA as well, so doing some work in that regard as well, to do some real-time searches and be able to quickly pass through the data as fast as we can.
Always exciting to hear new things coming out from the Allen Telescope Array in this regard. I'm going to actually throw two more audience questions at you because there are a couple of really good ones here. Just to someone would like to clarify. Jason Good would like to clarify what wavelength we're talking about for this particular pulsar candidate.
This was the radio wavelength, so these are the longer the longest wavelength that you have. The radio wavelength at X band between 8 to 12 gigahertz.
Okay, okay. And I kind of like this one. This one's from Twitch, from Real Nauticam. What is your background and how did you get into researching pulsars near an active galactic nuclei?
Yeah, so I grew up in Houston, Texas, so I did not grow up in like middle of nowhere, rural, like some people. I grew up in the city, um, and I actually didn't get into astronomy up until the 8th grade when I started watching documentaries with my dad on like the science and history channels. Then after that, I applied to some summer programs during high school in astrophysics, and I think that eventually helped me get into um, a really great astrophysics program at Cornell University, which is actually where Carl Sagan used to be a professor. So that was very
Hmm.
special. And it was there where I worked with a professor named Jim Cordes, who is very well known in the Pulsar community. And so I did a project with him on radio pulsars, and that's where my interest got piqued. I thought they were just very exciting for that precise reason that they serve as cosmic clocks. Unlike other types of astronomy, I think radio astronomy is really cool because it's a small niche, it's a small group of people doing this around the world, and so you can actually like take your own data, learn how to take observations, and then analyze your own data, which I think is unusual to other types of astronomy where you kind of just go through the archive. So it's nice to kind of see a project from start to finish.
I like
Yeah.
that. I like that. Well, so let's take one final question from me. What excites you most about studying the Galactic Center?
Yeah, so like I said earlier again, I think the Galactic Center has many exciting things happening. It's the most energetic region, and I think um it's the most exciting region, and I think there's lots of interesting things there waiting to be discovered with the right technology and the right sensitivity. And specifically, it would be amazing to find a pulsar near the Galactic Center. I think yes, that's like a holy grail, right? Whoever detects and confirms and times a pulsar around the Galactic Center would probably win a Nobel Prize in the future. So that's a really exciting scientific project for me and anyone else.
Yes, absolutely, 100%. And I think that's very exciting for both science and for you. And I love that for you, and I hope that that happens. And I will be cheering when you get your Nobel Prize in the future. Um, so thank you for
We're
joining
still
me
quite far from
today.
that.
I know. The science is a long game. So thank you for joining me today, Karen. Congratulations again on the postdoctoral fellowship, and welcome to SETI.
Thanks, Beth. Yeah, and thanks for everyone from all around the world for tuning in.
Yes, very appreciated. Thank you, everybody, for being here. If you enjoyed this conversation, please do the things, like it, share it, comment on it, subscribe to our YouTube channel. I'm trying really hard to hit the next milestone, which would be 100,000 followers. Please, please, please. Subscribe. Make sure that you get notifications for more space science interviews like this one. Next week, we're going to have something a little different, a little special. SETI Air director Bettina Forget will be joined by artists in residence Daniela Brill Estrada, Bart Kuipers, and Julie Michel Morin. Their project, Exoplanetary Poetry, transforms exoplanet atmospheric data into poetry using an AI that they have built. And now they're turning that poetry into science experiments. So this is going to be really cool and pretty fascinating. So stay tuned. And as always, we are the SETI Institute, a 501c3 nonprofit. Your bits, your subs, your super chats, your stickers, all of these things go to this program and help us keep it running and bring on more fantastic guests. I am lining them up left and right now. So hopefully I will have everything booked through the end of March soon. And we've got some really cool things coming on, I think, Titan and some radio interferometry. And I mean, it's a mixed bag of stuff. So make sure that you join us and help us out here. If you are inclined and able, a larger donation at our website, SETI.org, and clicking that donate or give now button. And also to keep in touch or to keep informed on what's going on here, we have a newsletter called Journey, and that comes out once a week, and you can sign up for that at our website as well. So make sure you stop in and take a look. We got a fairly amazing website these days, so come and check it all out. Until next time, everybody, keep looking up and stay curious.